One sentence to anchor everything. Message pack decoding is a tiny virtual machine that reads bytes sequentially, just like a CPU pipeline reads instruction from memory. So it's just a software that like encode the format of your data and persist it to the database engine. Everything below is just making that sentence precise. First, how did the first byte become 0x83? I didn't see that in the diagram. You actually did see it, but the diagram assumes you already know message box rules, where 0x83 comes from mechanically. The JSON object is open semi-curly bracket username colon quote Martin comma next line quote favorite number colon 1337 comma next line quote interest colon uh, argument quote daydreaming comma hacking closing semi-curly bracket. That is an object with three key value pairs. Message pack has a rule called fix map pattern 1000xxxx, meaning quote this is a map object. Pattern xxxx, meaning number of fields 0 to 15. Now encode object 1000 3 fields 00111. Combine bits 1000 0011 equals 0x83. So the encoder produces 0x83 before anything else. The diagram doesn't derive it. It shows the result of applying the spec. Second, how did you include 1337 must use 2 bytes? This is not arbitrary. It comes from message pack's integer encoding table. Message pack integer rules simplified range 0 to 127, encoding 1 byte, positive fixed int, range 128 to 255, encoding uint 8, 1 byte plus marker. So this uint 8, it's not like the UTF-8 where the JSON are encoded. It's a different, but it's part of the integer rules of message pack. So unit 8, 1 byte plus marker. 256 plus 65535. Unit 16, 2 bytes plus marker. Bigger, uint 32 slash uint 64. So that's why we get uint 16 because it ranged from 256 to 65535. And that's how the message pack integer rules are designed. Now check 1237 is greater than 255. 1337 is less than 65536. It must be uint 16. So message pack emits CD0539, CD equal uint 16 marker, 0539 equal 1337. This is data dependent, not guesswork. Third, opcode bits. Instruction class map to this discussion. You asked to relate this specifically to what we discussed before. Here it is. Message pack byte equals CPU instruction header, CPU opcode, message pack top bits, CPU addressing mode slash immediate, message pack bottom bits, operands, CPU operands, message pack following bytes. Example 0xA8 equal 10101000, 1010 string 1000 to length equal 8 bytes. This is identical in structure to add rux comma IMM8 where opcode says add, immediate says use next byte as the value. Fourth, if it's greater than 15, does it automatically use map 16? Yes, and this is critical. Map encoding decision logic. If fields less than or equal 15, colon next line use fix map 1 byte, next line else if fields less than or equal 65535, colon next line use map 16, argument 3 bytes total, next line else colon use map 32, argument 5 bytes total. This is variable length encoding. So the variable length is that it will go to the different ranges or it will instantiate another bytes when it doesn't fit on that first category criteria. Same idea as CPU instruction prefixes, UTF-8 characters. So this is like kind of like the text string encoding of PostgreSQL. So this is how JSON are encoded in PostgreSQL. Protobuf variants. Fifth, how is this variable length encoding related to the inside the machine? Inside the machine doesn't talk about message pack directly, but it absolutely explains the principle. Relevant chapters, important, chapter 4 to 5, instruction decoding, chapter 7, instruction fetch and decode stages, chapter 9, complex instruction formats. So these complex instruction formats is basically how different execution units in different pipelines are being fetched. So you're gonna see there when we discuss that in the future how the pipeline are, if not being fed by an instruction, is useless. Basically, you need to keep that pipeline. You need to avoid the pipeline stall. So that's just the instructions. What the CPU can read. x86 instruction are variable length. Start with opcode bits. May have prefixes. Decoder figures out instruction length before execution. Message pack decoding equals software version of x86 instruction decoding. So this message pack decoding is kind of like a software version of instruction decoding from compiler to the CPU. So it's a variable length as well. Start with opcode bits, may have prefixes. So this organization from the start kind of like allow this software decoding and encoding format to be able um, to react predictably. So six, it's the same with hardware. Why does 0xA8 not show 0 on the left? Hex digits already imply 4 bits. A equal 1010, 8 equal 1000. So 0xA8 already contains the leading bits. There's no missing 0. So A is equals to actually 1010 in the A8. And the 8 means 100 in binary. So 0xA8 already contains the leading bits. There's no missing 0. And that's also how we define right using type length value encoding. So strings are 8 bytes, not bits, correct? Username is 8 bytes, character USERNAME, each ASC2 char equal 1 byte. So 8 characters equal 8 bytes. Message pack never uses bits for strings, only bytes. 8. Where do spaces and line breaks come from later? They do not exist in message pack. This is crucial. Message pack stores data, not formatting. When browser API UI Pretty Printer renders it, they add formatting. So you get a raw data in message pack, not formatting. Basically, it doesn't have like the UTF where it also keep the some of the space formatting, etc. of JSON. Just like CPUs don't store white space, pretty printers add indentation later. So CPUs don't also store white space, right? They only execute pure instruction. So it's the same with message pack. Pretty printers and add indentation later. Number 9, what is a map? In message pack terms, map equal to key to value structure equivalent to JS object, Python dict, hash map, JSON object. So map 3 equals to open semicolon bracket, next line key 1 to value 1, next line key 2 to value 2, next line key 3 to value 3, closing semicolon bracket. Then, is this like x86 instructions fetch into L1 cache? Yes, this is the correct analogy. CPU L1 instruction cache, message pack byte buffer, CPU program counter, message pack pointer, CPU instruction decoder, message pack decoder. CPU execute, message pack, build data structure. 11. How does this help branch prediction? Because JSON parsing must scan for quote, or the quote, the double quote, must handle escapes, must guess string termination or the next line. Many branches, message pack parsing, length known upfront, no scanning, no guessing, straight line code. Fewer unpredictable branches. CPUs love this. 12. What is the pointer? Not a node pointer. It's just current underscore byte underscore index. Example, buffer equals 0x83, 0x88, 0x75, dot dot dot. The next line, PTR equals to 0. So decoder logic, read buffer, argument pointer, next line PTR plus equal 1, next line read next n bytes, next line PTR plus equal n. This is exactly like a program counter. 13. How this relate to structs, arrays, list, binary formats produce memory layouts, known sizes, sequential access, no pointer chasing. This enables cache locality, SIMD prefetching. So this data encoding format is the same with the column storage bitmap. It has known sizes, sequential access, and no pointer chasing. Unlike JSON, in JSON you have object and then fields, so you have a lot of pointer chasing. JSON to heap allocations to pointers everywhere. 14. Who scans JSON for codes, compiler, or x86? Neither. It's the JSON parser, which is a program written in C/C++/Rust/JS running on the CPU. The CPU executes instructions, do not understand JSON. So it is parsed already by the compiler when it gets to the CPU. By the time it is in the CPU, it's raw data. So JSON parsing is a software level decoding, not hardware. Actually, that's inside the Chrome. Chrome has built-in JSON parser. That's also we also discussed how those reason is the reason why JSON is the most commonly used encoding format, because it is supported by browser. Is the program counter an in-memory data structure like an array or list? No, but it points into them. What program counter PC actually is? The program counter is a CPU register. It contains a memory address. That address points to code, instruction, or data depending on context. So it fetches the code and data in the instruction queue. The PC does not store array or list. It stores where to read next. So the program counter in the CPU store where to read next. It doesn't know exactly what the value it will execute. Its entire job is to put the instruction in the instruction queue. Analogy that is exact, not hand wavy. Memory, next line 0x1000, 0x83, next line 0x1001, 0x88, next line 0x1002, 0x75. Next line PC equals 0x1000. The CPU first uses PC to fetch bytes from memory. So it fetched the bytes from the compiler to memory to get into the raw data, because the way for us to transfer data from in-memory data structure and then to bytes and then to CPU is using compiling those bytes from memory to our actual CPU L1 cache. Because remember the pattern or the structure is that you get you start from disk and then memory, then L1 L3 cache to L2 cache to L1 cache. The CPU uses PC to fetch bytes from memory. Second, decodes them. 3, advanced PC. So it decodes that the CPU decodes it, but it uses PC to fetch bytes from memory to instruction queue. In instruction queue, it decodes that and then advance the PC register to get the next bytes that it will fetch to the CPU, and that's it. Seconds, does message pack have a program counter? Yes, but in software, not hardware. In a message pack decoder, you will literally see uint8 underscore t asterisk ptr semicolon. It means pointer into byte buffer, or in JS, let offset equals 0 semicolon. This is software equivalent of the VC. Third, what code process JSON and message pack in real world? JSON examples, SIMD JSON written in C++. Next line, rapid JSON written in C++. Serde underscore JSON written in Rust. JSON that parse used by browser written in C++ inside V8. Message pack example, MSG pack-c. So these are the syntax. MSG pack-rust. So these are the syntax that you would use to use those JSON parser, and then at message at msgpack slash msgpack JS still logic driven. They're normal programs written in C slash C++ slash Rust slash JS. For why did you say the parser is running on the CPU? Because everything runs on the CPU unless it's hardware accelerated. Because another thing is that the parser would need to be compiled, right? I mean, those eventually need to compile in two instructions that could execute by CPU for you to do something. I mean, for you to transform that data. So, important clarification: the parser is not inside the CPU die. It's just a software before the program counter. It's not part of the instruction fetch unit. It is a user space program compiled into machine code to be fetched to CPU, executed by the CPU pipeline. Fifth, does JSON get converted to assembly before entering the CPU? So imagine this, since let's say you have like a code in bytes, or fetch in bytes, whether it's message pack, UTF-8, and you also have data. The program counter will fetch that to the CPU to execute that instruction to data, and then transform and then get back to a register, then transfer it with bytes again, and then render to the browser. So does JSON get converted to assembly before entering the CPU? Yes, indirectly. Compilation chain simplified C slash C++ Rust code to compiler C lang GCC Rust C. So as you can see, the C, C++, those are the programming language. I also Python and JavaScript near to the compiler, and it will be compiled, and then after compiled, it will go to assembly and then machine code, where the program counter fetch that data per byte that already compiled and already gone through the assembly. And then after the machine code execute, it will be loaded into memory. The machine assembly to machine code, which is still bytes, x86 bytes. It's not just the message pack bytes anymore. It's the different kind of byte, which is the x86, for it to be able to communicate to the abstraction of CPU. Then it will load it to the memory, and then L3 cache, L2 cache, L1 cache to fetch via program counter to fetch in the CPU, and then the cycle repeats. The JSON bytes themselves are data, not instructions. The parser instructions are what CPU executes. So those are different instructions. When you look at the CPU, it is parsing instructions, whether it's code or data stream. But if you look at JSON bytes, they are just data. It doesn't transform anything. Once it go past to the CPU, that's where it transforms something. How does pointer advancement actually work? Let's do literal code, not theory. Message pack decoding, simplified C. uint8 underscore tag equal buffer argument ptr plus plus semicolon. Next line, if argument tag n0xf0 equal 0xa0, open semi-curly bracket. Next line, int len equal tag n0x0f. Next line, char asterisk str equal n buffer argument ptr colon next line PTR plus equal then semicolon next line closing semi-curly bracket. That PTR plus equal then is the software PC Advanced. No guessing, no scanning, no branches per character.